So let's understand what does it mean. What does it mean by that the likelihood of the parameter W is equal to the probability of the observations or the probability of the data, right? So we have assumed that yi is generated by some function mapping like fw of phi of xi plus epsilon I. This is a randomized, zero mean randomized, right? And just for the sake of simplicity, we can consider that this is a linear mapping, although any choice of other choice of functions would hold, but let's just consider that this is the linear mapping is one such function basically that generates the data, right? So phi yi is phi of xi transpose times w plus epsilon I, right? So now let's fix a value of w, right? Let's suppose let's assume that the data is being generated in this fashion. It's a linear function of phi of xi. The outputs are the linear the observations. The output is a linear function of phi of xi plus some random noise, right? So let's assume that we select a value w hat, which is a vector of all infinities. Which is an n-dimensional vector. So all the locations, all the components of the vectors are infinity, right? And let's assume that yi's, that each of the observation yi's are finite, and assume that the phi of xi's are also finite, and so are xi's, right? So given that these are finite and the phi of xi is also finite and x is also finite, this value will almost always be infinity, since each of the components is infinity. Only some special case where everything cancels out, then this would be 0, but otherwise this would be either plus infinity or negative infinity, right? So again, yi minus phi of xi transpose w is equals to epsilon I. So now this value is either plus infinity or minus infinity, right? And the y is finite. It's not equal to infinity. Y is finite. So the difference between the observation and the prediction y hat and yi is lambda. Well, lambda is infinity. So the epsilon I will have to cover that, right? So epsilon I will have to assume the value of lambda, right? So in this case, lambda is infinity. Now for any particular distribution, let's assume that the probability distribution function for epsilon has only one mode, right? That is, it has just one maxima, and we assume that's a zero mean distribution, right? So let's assume that the distribution looks something like this. It's a zero mean, so it will have its peak at 0. So this is the axis of the this is a probability density function. So what is the probability of what is the p of epsilon being infinity, plus minus infinity? It is 0, right? So now all the values for all the i's, for all I, the difference lambda I is plus minus infinity, right? So each of the epsilon I, which is goes to lambda, is either plus infinity or minus infinity. Only in some special case, it would be small number when this thing is 0, which means all the components like cancel out each other. Some of the components are positive, some of the components are negative. But for almost all the other data points, it will either plus infinity or negative infinity, right? So what's the probability of all these observations, right? So probability of yi given xi parameterized by the w, the value of w, which we assume that w hat. So these are almost all, for all these probabilities are almost 0. So the probability of this observation is 0, given the choice of parameter. If W hat was the optimal parameter, right, then we see that the probability of the observations in the data is close to 0 or almost 0, right? So what it means is that the farther the W from the optimal solution, so as we move towards the optimal value of the parameter W, that is W star, as we move from the non-optimal to the optimal W star, each of the lambda i's, there is a differential prediction y hat I minus yi, will keep on reducing, right? And for the optimal, it would be minimal, right? For all the points, right? So it means that the bad choice of W will have this probability being close to 0 or almost 0, right? But a good choice of W will increase this probability, right? So that is why we say that the likelihood function, that is the likelihood of the parameters, right, is directly proportional or equal to the probability of the observation in the data. So the optimal choice of the parameter W is the one that increases this. So likelihood function is a measure of goodness of W. So the better the value of W, the more closer it is to the optimal, the higher would be the probability. So if we maximize this likelihood function, right, then we'll get, if we maximize the likelihood of the function, we'll get a parameter value W star that optimizes or that attains the maximum value for this that maximizes the probability of the observation of all the samples in the data, right? And this is what we are going to use. So next we'll consider, so if you maximize, that's why we call it the maximum likelihood estimate of W, right? So W star is the maximum likelihood estimate, or MLE for short, because it is obtained by maximizing the likelihood function L of W. And this is what we are going to use to further derive the maximum likelihood estimate of our parameter W, with some assumption on the distribution of the random noise epsilon.